In this video, we will analyze the fifth harmonic notes that were described in an earlier video. We start by sorting each interval, the 5V notes, the 5F notes, and 5E notes, in descending order of the length of their conical radius for each of the conics. This first table illustrates each interval sorted individually, and this next table shows all three intervals integrated and sorted in descending order. These following illustrations show all the conics for each interval drawn on a sphere for visual comparison. These are the 6 5V note conics drawn on a sphere. These are the 8 F note conics. And here are the 9 5E note conics. And finally, this is the integration of all 23 fifth harmonic conics drawn on a sphere. This was my first attempt at analyzing the fifth harmonic notes, and I soon realized I was limited by the accuracy of my measurements for the conical radius of each conics. So I decided to geometrically derive the exact values for the radius and angles for each of these harmonic notes. I decided to focus on the conical angle omega and subtended angle theta as seen in this diagram. This diagram was shown earlier, and it shows the relationship between the angles and the radius of the conics. I will be referring to this table of solutions for angle theta, and this will be the basis for the rest of the analysis of these fifth harmonic notes. Let me explain what kind of ratios that I was looking for. I used the basic concepts from music theory to categorize the ratios, where the ratios are a difference in pitch between two sound waves. These intervals are also expressed as small integer ratios and represent notes on a scale, as seen here, for example. These ratios are described as intervals that are known as perfect, minor, and major, as seen in this table. While I'm not implying that spherical harmonics have musical properties, this music terminology was a good match to classify the angular ratios. Now that I had derived the angular values, I could search through the results looking for small integer ratios between the angles theta and omega, which are the subtended and conical angles for each harmonic note. Some more complex ratios were discovered and be discussed towards the end of this video. Let me start with the small integer ratios, which are displayed here in table 10, that show the theta scale and omega scale. Now let me explain what I mean by that. There were 4 5E notes that have some simple ratios between their angles theta, which were derived in the previous table, and they were simple fractions of pi. The largest angle was pi over 2, and this is set as unison, or 1 to 1, and the other 3 angles were compared to unison and resulted in the simple ratios seen here. For the omega scale, the largest angle was 2 pi over 5, and that was set as unison, or 1 to 1, which was then compared to the other 3 angles, which also resulted in some simple integer ratios as seen in this table. The results of the theta and omega scales are integrated into the interval ratio table seen earlier, and 7 of the 8 ratios fell within the boundaries of this table. The ratio of 5 to 2 was one of the outliers. Now in the next section, I'll describe some more complicated ratios that I found. Before I describe the next interval or scale of ratios, let me show you how the angle theta will be described and processed. Theta is the subtended angle of a harmonic note, and theta of any note can be represented by this nomenclature. The angle theta can also be represented as the inverse cosine of some fraction x over y, And in such cases, the cosine of theta is equal to that fraction itself, x over y. And for these cases, the ratio that I have found are ratios of the cosine of the angle theta, or a ratio of ratios, since cosine is a ratio itself. Let me describe some of the more complex ratios that exist within these values of theta. Many of these angles can be represented by the inverse cosine of some simple fractions of integers and square roots. As a result, I can first transform these values with a cosine function to extract its operand. Then I would proceed to do a ratio comparison on these operands, and the results can be seen in a cosine scale column in Table 11 as ratios of integers and square roots. This doesn't appear to have any musical properties. Perhaps it may represent some other properties in nature. Before I move on to the next scale, I wanted to elaborate on something. Here I added an extra column to Table 11 for the value of cosine theta. And one can see that the ratios are easy to visualize as a cosine of one angle divided by the cosine of another. But notice, as I replace these simple representations with the actual decimal numbers in each column, that the ratio becomes less and less obvious and harder to find from a visual perspective. Table 12 shows a similar complex ratio that is based on the sine scale, and in a similar fashion, the operand of the inverse sine function can be extracted, and its ratios can be seen in the sine scale column of Table 12. The tangent scale is a bit more complicated and consists of two parts. There is a tan scale, shown in Table 13, that results in the ratios of integers and square roots. Then there's the phi scale, or golden ratio scale, shown in Table 14, where the ratio of its operands are algebraic fractions of the golden ratio, and where the golden ratio is equal to 1 plus the square root of 5 over 2. This next ratio scale is even more complicated than the previous scales, and I've referred to this as a complex scale, as shown here in Table 15. Let me use this representation as an example to describe the ratio. The ratio is between the length of the conical radius RTA of two different notes, where this ratio is also equal to the sine of the subtended angle theta of some other note. The note 5e lower 2e is a unison note for all ratios, and then I can step through each of the other notes that are the numerator for subsequent ratios. I've shaded the numerator for each ratio in green and the resulting sine function equivalent in yellow. I'm not sure if this has any significance in the physical world, but it was an interesting and unexpected result. Here are just a few examples that show how several harmonic notes can be integrated together on the surface of a sphere and create some interesting patterns. And I've referred to these integrated harmonic notes as harmonic chords.